Matt, you're muted.
Good evening. Tonight's presentation is going to be given by David Chandler. David has been an avid sky watcher for decades and is an active member of the Denver Astronomical Society. He is known for inventing the night sky planisphere, a ubiquitous tool, star-finding tool that astronomers around the world use to spot stars and constellations in the night sky. David has taught physics, math, and astronomy since 1972. He has written extensive astronomical software and also wrote Exploring the Night Sky with Binoculars and co-authored Sky Atlas for small telescopes and binoculars. He has made several telescopes and currently owns a 13-inch Coulter-Dobsonian telescope. David, please proceed with your presentation.
Hi, my name is David Chandler, and the goal of my presentation tonight is to help you understand planetary motion as seen from the Earth. So like, how could you understand the motion of the planets as you see it from your backyard, for instance? Here we have a picture of Mars over a period of time. The planet is moving from right to left on the average. So like, it's moving along here, and then it goes backwards for a while in what's called retrograde motion, and then it goes prograde again, or forward again. And so forward on the average is from the west to the east. And in the sky, by the way, west refers to the western horizon. So over here would be, in this direction would be the western horizon. Over there is the eastern horizon. So we're sort of standing on the Earth, looking sort of southward, and we're seeing the motion of the planet over a period of time. So this is like a series of photographs taken over a bunch of days, probably a month or more. Okay, I don't know if you recognize it, but there's a few constellations in here. Right here is the head of Leo, the lion. So that's the backward question mark, or the sickle, it's called. And that's the head of Leo. Here, this little cluster out in front of Leo is called the Beehive Cluster. It's in the constellation Cancer. Cancer is a very faint constellation. There's this little boxy thing right here, and then a couple of other stars off to the side. But basically, the Beehive Cluster is the most noticeable thing in Cancer. But the other thing to notice is we see the planet changing in brightness and size, apparent size. So when it's in retrograde, it looks brighter and larger, and literally it's closer to the Earth at that time. And so we're actually seeing a little bit of a three-dimensional effect here, because as it sweeps from right to left and then coming around, it's actually approaching and receding from the Earth as it goes. Okay, here I've constructed, using a tool I have called GeoGebra, I've constructed an animation of the solar system as seen from above, looking down from far out in space. And we have circular orbits, so I've really simplified everything here. The point here is not to do accurate predictions of positions, although this will get you sort of ballpark close. But the purpose here is to understand the nature of the motions. That's the goal here tonight. And in particular, let's just focus on one planet at a time. And we looked at Mars just a minute ago. Let me put that on here. There's the line of sight when we're on Earth looking at Mars. And notice when the Earth passes Mars, that line of sight reverses directions. So in general, the line of sight is sweeping around here counterclockwise around the sky. And then every once in a while, when the Earth catches up with Mars and passes it by, it's sort of like when you're on the freeway and you pass another car by, even though you're both going forward at high speed, it looks more or less like the car beside you is actually backtracking. So here we go again, and Mars looks like it's the line of sight is reversing direction right there. So apparently the key thing is the relative motion of the Earth and the planet, and then this line of sight goes back and forth as a result. Let's look at Venus instead. Now here we come around, and again counterclockwise, except right there. And notice in this case Venus is passing the Earth. And if we keep on coming around, that line of sight is rotating counterclockwise, and Earth is going to catch up to Venus. Actually, no, Venus is going to catch up to the Earth. The inner planets move faster than the outer ones. And so here comes Venus. And there we go. As it goes in between the Earth and the Sun, it backtracks. Okay? And so by backtracking, it's like this line of sight rotates clockwise. And that's a brief interval, and then it returns to its average motion. Okay. Let's see what this kind of motion looks like if we pin down the Earth instead of pinning down the Sun. In the ancient world, they thought of the Earth as the center of the universe, and so they saw the Sun and the planets all going around the Earth. And one of the things you learn in physics is how you describe the way things move depends a lot on your frame of reference. In other words, what is it you're going to consider to be fixed? So the world, as observed from a moving train, looks a little different than if you're standing on the platform, for instance. So let's change the picture and let's pin down the Earth and see how these planets move in that situation. Okay, here I have two views of the solar system, and if you look at them carefully, you can see that they're in the same relative positions. Here's the Earth, down a little bit is Venus, over here is Mercury, and over here is Mars, just like it is over here. I've added the Sun here. We can add the Sun in a few minutes here, but I want to see just the planets by themselves to start with. Okay, so let's let these things go. And I am tracing out the motions through the space here on this view. And it looks very different. Here they're going in circles. Here they're going in all kinds of loop-the-loops. Let's look at the lines of sight. And let's pause it. And notice that Mars is off to the right here. And then Mercury is up at this angle right here. And Venus is here. And as I let the thing run, notice that those lines of sight remain identical the whole time. These are two completely equivalent descriptions of the motion, except for the fact that in one case we've pinned down the Sun, and in the other case we've pinned down the Earth. So how we view the motion depends on the frame of reference we use. Are we going to have a geocentric view, in other words, an Earth-centered view, or a Sun-centered view, a heliocentric view? Okay. This view is actually older. When they originally thought the Earth was the center of the universe, this loop-the-loop kind of behavior was very puzzling, and a guy named Ptolemy came up with a system to try to interpret this. The way he did it was, he said that these planets are moving on circles that themselves are going around the Earth. So the little circles the planets are actually moving along are called epicycles, and so they're not really primarily going around the Earth. The epicycles are going around a point that's going around the Earth. So let's add these epicycles in, and I have those in red. And then the centers of the epicycles I have tracing out these green circles around the Earth. Let's see how that works. And again, we have that loop-the-loop kind of complicated motion, but Ptolemy really simplified it all because you can actually account for all of the complexity by just having circular motion. So here's Mars going in a circular path around a point, which itself then is going around the Earth. So yeah, it's complicated, but it's a whole lot cleaner than just looking at the paths themselves. Now, what Copernicus did when he came along was he did a very simple transformation. He simply moved the center point from the Earth to the Sun. Now, why was that such a big deal? This is considered the beginnings of the modern world. I mean, it's the beginnings of a huge scientific revolution. If you think about it, there's a lot of implications besides just, is it in the Bible or things like that. He had a lot of problems. He would have had a lot of problems with the church. His followers had a lot of problems with the church at the time, because as long as the Earth is seen as the center of the universe, the Earth is special. It's not a heavenly body. It's something earthly. It's distinct from the things that are going around on the outside. So you can think of the Earth as made of earthly materials, earth, air, fire, and water. And then there is a totally different kind of substance that follows totally different rules of behavior out here in the heavens. And so this heavenly material, sometimes referred to as the ether, think of the word ethereal, and sometimes it's referred to as the quintessence, the fifth essence, earth, air, fire, and water down here, and a fifth substance of which the heavenly bodies are made. So it seems like the Earth has a special place in the universe as a not actually being part of the celestial region, but it's actually down here on Earth. And so theologically speaking, the Earth is unique. And so the whole message of the Bible and all that is referring to this unique place in the universe. As soon as you take the Earth out of the center, all of a sudden what you're doing is you're turning it into one of the heavenly bodies, and you're turning the other heavenly bodies into potentially other Earths. Like, immediately it brings to mind, are there other civilizations out there? What's so special about the Earth? Why was the whole, the plan of salvation that the church talked about, all of that, why would that relate to this one little speck in the universe rather than, when it's a unique body here in the center? So it really threw a lot of things up in the air. By the way, it even threw physics into a tailspin, because here, when you had the Earth at the center, that was an explanation for why do things fall. Well, heavy objects, Earth-like objects, have a tendency to accumulate at the center of the universe. So the natural motion for a heavy object like a rock is at the center, and if you let go of it, it will move toward the center. Out here, the Earth is no longer at the center. So why does a rock fall to the Earth? Why doesn't it fall to the sun instead? So what's going on here? We had to come up with a totally new understanding of gravity. And so the whole idea that bodies in the universe attract each other was a brand new conception, and that was left to Newton a couple of generations later. So it started the ball rolling to a complete overhaul in the physics, as well as upsetting philosophy, theology, and all these other realms. Copernicus got off easy because he didn't publish his results until he was on his deathbed, so he didn't take the heat for his ideas, but his followers did. Okay, what I've done now is I've zoomed out, and here I'm looking at the outer planets just for completeness here. And so this is Mars again, and here's Jupiter and Saturn. I'm only going out as far as Saturn. These were the planets that were known back in Copernicus's day. And let's put lines of sight on there. Notice we still have that same property, that the lines of sight are the same, just we have a different center point. And I'm also going to add on the sun. And so here's the sun, which also goes around the Earth, but just as a simple motion here. I could zoom in a little bit perhaps to make this a little bigger. Okay, let's run it and see what we see. Okay, so again, we have these little loop-the-loop curlicues, retrograde motion and the like. And let's add in the epicycles. So if I look at the epicycles for the outer planets, we can start to see that there's a little bit of interesting regularity. This isn't quite the way Ptolemy arranged things. He had things spaced out a lot further, because here, notice the epicycle for Mars. Mars would be crashing past Mercury and Venus, and you can't have that because he thought these planets were embedded in crystal spheres, and so, you'd be breaking the glass, so to speak, if you had them intersect. And so, since he didn't really know how far away they were, he just pushed these outward along these lines of sight until these orbits did not affect each other. But let's just leave it like this for now. Notice that, at this scale at least, notice that this epicycle, the relative orientation of the center out to the planet, is the same for all of these. And in fact, it's the same as the Earth to the Sun distance there. All right, so here's the Sun going around the Earth in a simple circle, and these epicycles have the same size and in fact synchronized circles that they're doing. Let's run it a little bit more. In fact, let's take those lines of sight off. Those are a little bit distracting. Look at those epicycles, the way they line up. Okay. Now, the way Ptolemy had it when they were out at different distances, the epicycles were not all the same size, but it still had this property that they were parallel to this Earth-Sun kind of an orientation. So you might see how Copernicus could make the link. It looks like the Sun has something to do with the motion of these planets, because why are these things all syncing up with the motion of the Sun in the sky? And in fact, he came to see this as a simple shift in perspective would cancel out the epicycles here for these planets. Okay, everything we've talked about so far is material you'd get in a standard astronomy class. You have the Copernican system with the Sun at the center. You have the Ptolemaic system with the Earth at the center. But I had a different project in mind, which is, how do you see the planets as seen from the Earth in relation to the Sun? Because you want to see the orbits around the Sun. So you want to essentially visualize a Copernican universe from the Earth. Okay, how do we get both of those worlds to cooperate here? And so what I have on the right side here is a little diagram of a person standing on the apparently flat little chunk of Earth, and the sky above, and the Sun is out there. And the question is, how do the planets move in relation to the Sun? Because you want to see the planets going around the Sun. Okay, now here's the Copernican view on the left, and let's just let this run for a little bit. Okay, so notice you have the Earth moving around, and you have each of the planets moving, and the Sun has been pinned down. But over here we want to pin down the Earth, because that's going to be a fixed point. That's right there below our feet. So let's start by just following the Earth here. An assumption in the background that we've had up to now, both for the Copernican and the Ptolemaic system, is that the stars remain fixed in the background. That we're plotting the motion of the planets on a star map. And so it's the motion of the planets relative to the stars that we've been looking at all this time. And that's true for both the Ptolemaic and the Copernican system. So what we want to do here is, instead of look at motions relative to the stars, we want to look at motions relative to the Sun. So if we're on the Earth here, notice that Mercury and Venus are both in the more or less general direction of the Sun, except they're oscillating back and forth ahead of and behind the Sun here. And here comes Venus going across the line. Now, this can be made a little bit easier to see if we pin down not only the Sun, but also the Earth. I'm going to pin the Earth at a fixed position in its orbit. So our coordinate system now is going to be rotating. The stars are going to be rotating in the background because I want to keep the Earth fixed. And so we're just basically moving with the Earth here. Let's do this. Let's run this back to 0, starting with all these things lined up here, basically. If I start just by hitting go, notice that we have Venus and Mercury getting out in the lead, and Mars is lagging behind. And here's the Earth. But if we rotate the chalkboard, so to speak, in other words, we're going to keep the Earth fixed, the fact that the Earth is getting ahead of Mars can be seen as Mars actually going backwards, because it's the combined motion of Earth and Mars that we're portraying here. Let's go on a little further and notice that Venus and Mercury have gotten further ahead. Mars is actually moving backwards like this. If I take it out of that rotating frame of reference, Mars is lagging more. In this frame of reference, Mars is actually moving further in this direction. So that's what we're doing. We're using a rotating frame of reference to see the planets. We're ignoring the stars entirely, and our point of reference is the sun. So we have a fixed Earth and a fixed sun. And now we can actually see the planets as they are moving in relation to the sun. Now, let's do this. As these things go around, notice that we have simple circular motion here. And it's just that Venus and Mercury, which are inferior planets, they're called, they're the planets whose orbits are smaller than the Earth's orbit, are going in the same direction we normally expect, but slower. Mars, and this is typical for the outer planets, Mars, Jupiter, and Saturn, also known as the superior planets. Nothing special about them. They're just that they're further out than the Earth. And they are just moving in a circular motion in the opposite direction. And that's just an artifact of rotating the chalkboard to keep the Earth fixed. Now, the interesting thing about this frame of reference is this is the frame of reference if you go out in the backyard and look up. So let's say we have the Earth fixed beneath our feet. That's why we have the Earth fixed. And if I went out every night at, say, sunset, here's the sun in the west, say going out at 6 p.m., and we're keeping the sun fixed just like we are here. And so if you don't look at the motion of the planets as they move during the evening, which is mostly due to the rotation of the Earth, but just look at them from one day to the next, how do their motions progress? Okay, so let's look at them one at a time. Let's start with Mercury. And notice that over here we see Mercury going around the sun. From the backyard, what you see is Mercury oscillating with respect to the sun. Now here it's up in the evening sky, and down here it's in the morning sky. We say that because if we turn our Earth around until we're in the morning hours, so here we are at 6 a.m. instead of 6 p.m., notice that when Mercury is on this half, it's up in the morning sky. And then if it's up in this half, it's up in the evening sky. If we go out at midnight, we're never going to see Mercury because it never gets over here. It's always in the direction of the sun, never outward from the sun. Okay, let's go back to the evening sky. I think I use that in preference because that's mostly when I do my observing. Let's go to Venus. Notice the Venus is doing something very similar to Mercury. Here it goes in the morning sky, and then it's coming up around the far side of the sun, so it's slowly emerging into the evening sky. And when it gets around to the point here where the line of sight is tangent to the orbit, let's pause it there, right there. This is called greatest elongation. In other words, the elongation is the angle between the sun and the planet. So this is greatest elongation in the evening sky Down here would be greatest elongation in the morning sky. And you can see that translates directly into what you see outside at night. So the inner planets are very easy to see orbiting the sun, because that's exactly what we're looking at here. So the oscillation back and forth. Notice how quickly Venus went from the evening sky to the morning sky, because it only went a short distance from the tangent point here down to the tangent point here. But then it takes a long time to go around the far side of the sun and come back up to greatest elongation in the evening sky. Okay. Now, the same thing happens for Mercury, although it's not as extreme, because the tangent lines here for Mercury are a little bit more closer to being symmetric. Okay. But again, long haul coming back around. And by the way, if you were to observe Venus at this part, any time when it's here beyond the sun, the sunlight is lighting up more or less the same face that you're observing. So if you look at Venus in a telescope, it's going to appear more or less full. It'll be gibbous, basically. So you see most of the disk just a little bit flattened on one side. However, if you go around here until Venus is starting back down towards the horizon here, notice that the sun is lighting up a different angle on Venus than what we're looking at. It'll look like a quarter moon type of appearance at greatest elongation. And once it passes that, it's actually going to look like a crescent, because it's mostly lighting up the far half of the planet, and we just see mostly dark disk and a little bit of a crescent around the edge. By the way, Venus is going to look huge when it's here because it's close to the Earth. And so what we can interpret over here in terms of our view in the sky is Venus is going to rise, and it's going to be more or less full, and it's going to be small because it's far away. As it gets toward greatest elongation, it'll be half illuminated like a quarter moon, and it's getting larger as it does so. And then as it zips back down towards the sun, and I say zip because it's going to go quickly out of the evening sky, it's going to be in a crescent phase at that stage. And so you actually can, in a telescope, actually see it moving around the sun, because the phase changes tell you where it is in relation to the sun, sort of in a three-dimensional kind of a sense here. Okay. Now, let's go to Mars. In the case of Mars, remember, we have in this coordinate system, in this frame of reference, we have Mars moving backward in this circle. It's just moving in a circle, but we are turning the chalkboard to follow the Earth. So from that frame of reference, Mars simply appears backwards. So as long as you can wrap your head around what we're doing to get this point of view, let's just watch Mars, and it's going to go around the sun. Right now, it's far beyond the sun. It's going to look small and faint, and as it comes around to here, there, this point is called quadrature, because it's a right angle. That's what that's referring to. Quadrature, like in a quadrilateral or a square, is referring to a right angle, basically. And so if the line of sight to the sun and Mars is at right angles. And notice it's 90 degrees from the sun in the sky. In this case, it's going to be visible in the morning sky. At midnight, it's just rising. It's just starting to enter the midnight sky. Let's go back to evening for now, just to have a reference point. And so if I let this run a little bit more, notice it's speeding up. Did you notice that it's speeding up? So from quadrature to quadrature, notice that's a short distance on its orbit. And around here is a long distance around behind the sun. And so this part of the path takes a long time, and Mars, as it goes around here, gets fainter, and because it's getting further away, and it's getting smaller in a telescope. As it comes here, the size is increasing in a telescope. If you want to see the surface details on Mars, it's best to see it when it's over here, close to the Earth. And so when it's close to opposition, opposition is when it's opposite the sun. So that's when it's at its closest to the Earth over here. Like there, that's close to opposition. And so opposition is when it's just entering the evening sky, but that's when it's overhead in the midnight sky. Okay? And continues around. So what we're seeing is the actual orbit of the planet around the sun in a Copernican sense, with the slight modification that we are looking at it from a point of view of a frame of reference that's rotating to keep the Earth fixed. Let's go for Jupiter, and let's go ahead and rotate with the Earth and let it run. So notice that Jupiter comes to quadrature a whole lot closer to just being the halfway point. So from quadrature to quadrature, yeah, this is shorter, and so Jupiter goes faster as it goes near opposition, but the difference between this side and this side is very slight. So it's going at a closer to being a uniform speed around the sky. And it, like Mars, appears to be doing this backward circle, but what we're actually seeing is Jupiter orbiting the sun. And if you took photographs of Jupiter over here near opposition, they would be somewhat larger than if you took photographs over here. Go out to Saturn, and it's even closer to being symmetric here. So here's where Saturn reaches quadrature, opposition, and then quadrature in the evening sky, and then approaching conjunction as it goes around to the far side of the sun. But notice the left half and the right half, yes, they're somewhat different, but not a whole lot. It's most extreme in the case of Mars, because in the case of Mars, we are closer to Mars than we are the sun, and so this is a very pronounced difference left to right. So that was my insight that I got by consciously seeking a way to understand the motion of the planets relative to the sun, like a Copernican view. So I don't have any epicycles here. There's nothing to do with the Ptolemaic system here, but we are still taking an Earth-centered point of view. So here's an Earth-centered point of view with the sun also held fixed, and we're ignoring the stars. Okay. By the way, what happened to retrograde? Notice that when Mars is in this part of its orbit, it's moving fast. And in fact, we can say it's moving westward faster than the stars appear to be moving in the background. The stars are moving in this frame of reference because we're turning the chalkboard. In order to hold the Earth fixed, we have to move the stars at one cycle per year. And Mars is speeding past them here. It's going faster than the stars are. And so therefore, we're in retrograde. Now, if we go around here until Mars starts to slow down, the stars are going to get to where they move faster than Mars is. Mars is being held back. And so Mars is appearing to drift eastward relative to the stars here. And so most of the time, Mars is drifting eastward. It's only when Mars speeds up as it gets close to opposition that it passes the stars by in its westward motion. And here it's in retrograde. All right. Now, we don't have any loop-the-loops in this point of view, but at least you can see the connection between this perspective and the Ptolemaic system. So the Ptolemaic system pinned down the Earth and held the stars fixed. The Copernican system pinned down the sun and held the stars fixed. What I'm showing you here is a way to visualize pinning down both the Earth and the sun. In order to do that, we have to rotate the chalkboard to follow the Earth to make sure it stays fixed. And from that point of view, we have the simplicity of circular orbits around the sun for the planets. And you'd have the one modification that the outer planets, the superior planets, appear to orbit backwards, but just remind yourself that's the fact that the Earth is moving around the sun faster than they are. And so that's where that comes from. Okay? So there you have it. You can watch the planets go around the sun. And there you have it.
Thank you, David.
Did you hear that okay?
Yes, we at least I watched it very clearly and heard everything.
I'm watching it very slowly along with the rest of you. I noticed a few flaws, like I left Saturn off of some of those images accidentally.
Yes.
I misspelled watching. Oh well.
Let me start the questioning with my simple question.
Okay.
How does the moon fit into this, into your diagrams? You sort of left it because you focused on the planets, but can you say anything about the moon?
Well, the moon goes around the Earth, so there's not that much to explain here. For the planets, it's the complication that if you take a Ptolemaic point of view, you got all these retrograde loops and stuff. And if you take a Copernican point of view, it seems like what you would see from far out in space, but it's hard to translate down to Earth. So that was the problem I was solving. The moon, it's a simpler problem, but it's a different problem. So I have an animation that shows the cycle of moon phases too, and sometime I can show you that. By the way, I have a website. If you go to my the stuff that I do for my math students and all that is called mathwithoutborders.com. And there's a bonus tab in the menu at the top. And if you go there, and if you go down there, I have that thing about the moon phases. You can see that right there, and some other things. Anyway, so I've done a lot of different things, but that's a different problem than the planets.
Right. Okay, I have some remarks or questions. Quite a few people are commenting that it's an excellent explanation, an excellent presentation, and very fascinating, and superb presentation from Jack. Now, I think Dina had a question. Why don't you pose the question, Dina, yourself?
Hi, Mehmet. Thank you. And thank you, David. That was wonderful. Excellent way to show it. Do we know if there were any other cultures that figured out the truth of a sun-centric movement of the planets before Western people did?
Actually, Archimedes believed that the sun was at the center, and he referred in his writings to Aristarchus, I think it was. Anyway, so I don't think we have any writings from Aristarchus, but we have a description of Aristarchus by Archimedes. Archimedes did this. He created a new number system out of nothing. He did not have access in his day to a number system where you could construct infinite, arbitrarily large numbers. You would run out of symbols, just like Roman numerals and stuff like that, right? But so he came up with it's more complicated than what we use today, but he created a number system where you could generate larger and larger and larger numbers. And to illustrate his point, it's called the Sand Reckoner, is the name of the essay he wrote. S-A-N-D, the Sand Reckoner. What he did was he calculated how many grains of sand it would take to fill up the universe. That was his demonstration project for the power of his number system. And in the process of writing that up, he explains how he figured out the size of the moon's orbit, namely using eclipses and things. He explains how he figured out the distance to the sun, which was a correct method, but bad observation. I mean, you know, there's impossible to get good enough accuracy in the observations. So he thought that the sun was 40 times farther than the moon. In reality, it's 400 times farther than the moon, but a tiny difference in his observation. Anyway, just understanding how that all worked. And then he, once he put the sun 40 times farther than the moon, he realized it was so much larger than the moon. And he knew that the moon was a quarter the size of the Earth. So that still makes it 10 times as large as the Earth. And so he figured, well, the sun must be the center. And so Aristarchus and Archimedes, they did think of the sun as the center from that kind of thing. And the thing that, you know, the amount of astronomy it took for them to figure out those kinds of measurements with no equipment, and they didn't even have, I mean, Kepler did all of his elliptical orbit stuff. He didn't even have a decimal number system. He used a base 60 equivalent of decimal fractions in order to avoid having to do the whole things with ordinary fractions. That's where we get degrees and minutes and seconds. Those are 60ths and 60ths of 60ths. So it's a base 60 equivalent of decimal fractions. Wow. So, I mean, these guys were absolutely incredible. I just took the attitude in my teaching, anything they did back then, a high school kid ought to be able to do today. So I had one of my students, for instance, figure out the distance to the moon using Archimedes' method and so forth. But yeah, so there were a lot of smart people back then. I mean, Archimedes was the biggest of the big as far as I'm concerned, but there were several of them.
But no evidence from like the Chinese or the Mayan civilization?
I don't know those well enough.
Okay. All right. Thanks.
Okay. Jim has a question or comments here. Jim, do you want to voice it yourself? You can unmute. No? Maybe I'll read it. He says, I have long wondered how and when the relative diameters of the orbits were discovered. So are you saying that they weren't known, but rather defined by Copernicus to be the sizes necessary to make the diameters of the epicycles to be identical? Is this right?
Well, Copernicus had the relative proportions of the orbital. They didn't have the astronomical unit measured precisely, but they had the relative distances to all the planets by Copernicus's time. You needed the heliocentric system to get that, to make that a meaningful question. So it would start with him. But the data was there even in the Ptolemaic measurements and things like that. So, but yeah.
Okay.
It goes back to Copernicus. And it took, you know, the first time, I believe the first good measurement of the astronomical unit was actually like measuring the orbital dynamics of an asteroid or something like that. In other words, coming up with, you have all the relative sizes, and then you need some size you can pin down and actually measure in kilometers or meters or whatever. And then you have it all. And there's various other measurements of the astronomical unit over time, but there you go. One of the measurements of the astronomical unit was the fact that when Jupiter is on the far side of its orbit compared to the near side of its orbit, the travel time of light between Jupiter and the Earth is different by 16 minutes. And so from that different, and then that offset the positions of the predicted positions for when the various moons of Jupiter would eclipse and things like that. And so I think it was Romer or something like that. I'm not sure. It's been a while. But then, so that 16 minutes is the diameter of the Earth's orbit in light minutes, So we're 8 light minutes from the sun. So that was one of the early measurements of the astronomical unit.
Okay. Are there any other questions? Jack says used Eros to help define AU.
Mm-hmm.
Yes, Roman
Yeah.
version. What? V of.
I knew it was one of the astro. I couldn't remember which one. Yeah.
Okay. And Jim asked again, how do the inclinations of the orbits fit in?
Well, they all have different orbits. I mean, each orbital plane is slightly different.
But doesn't it get reflected in the?
They're all pretty close to being flat if you exclude Pluto, which we have now excluded. But all the planetary orbits are just within just a very few degrees. And if you exclude Mercury, then the rest are just within a really small amount, you know. So Mercury is tipped, I think, several degrees, and all the rest are less than that, except for Pluto, like I said. Anyway, but I think you have to go back to evolution of the solar system to account for why we have coplanar orbits, or close to coplanar orbits for the, it has to do with the dynamics of all the particles that are interacting as they're, so the disk flattens, and as the particles coalesce into the planets, becomes orbits congealing out of a flat disk.
I guess in the simulation that you have, you are not reflecting that change.
Oh, no, I'm just flat. I have all kinds. I mean, hey, these are not circular orbits. Kepler proved they're elliptical orbits. They're not circular, all right? I'm using circular orbits just for simplicity because it was just the visualization thing that I was going for. I didn't want to muck it up,
Right. Yeah, he is saying that can you see or visualize the inclinations?
Well, that's, all of those secondary effects are there. I mean, bigger effect than that would be just the fact that the eccentricities of the orbits. Mars has the most eccentric orbit, and that's why basically Kepler, when he was questioning the circular orbits, used Mars because his mentor Tycho had told him that was the one that was hardest to explain. And so he figured he needed to use that as the most extreme example. And he basically showed that you could not fit a circular orbit to Mars within the accuracy of Tycho's observations. So I think the story I recall, and it's been years since I've taught astronomy, but I think it was Tycho's observations were good to like 2 minutes of arc, as I recall, or he was that precise in his observations. And Kepler showed that Mars, if you tried to fit a circular orbit to Mars, it would create errors. You couldn't get better than 8 arc minutes. And so since 8 arc minutes is outside the margin of error that Tycho's observations established, he discarded circular orbits because of that. I mean, that's pretty amazing too.
Okay. Are there any other questions? Well, thank you very much, David. And we really appreciate your presentation. So thank you.
Yes, it was wonderful. Thank you.
Okay, well, go look at the planets.
Are there any other questions? Well,
somebody with a furry face is giving a thumbs up there.